Now that we've covered the background, let's talk a little bit about what relative importance analysis is and what's going on when it's performed. Relative importance analysis is something that should be looked at as a supplement to multiple regression, not a substitute for it. It supplements multiple regression analysis by permitting variance to be accurately attributed to predictor variables that are correlated. So you may find that relative importance analysis yields results that differ somewhat than what your multiple regression analysis suggests. Now, that difference is likely to become greater as the collinearity amongst your predictor variables increases. It can be helpful to understand what it is that the relative importance term stands for. Okay, so that term refers to the contribution a variable makes to the prediction of a criterion, a dependent variable, by itself and in combination with other predictor variables. What that means is that you're able to determine how much of the variance in the dependent variable is uniquely attributable to each predictor variable. The nice thing about relative importance analysis is that the computer and the software will do all of the hard work. We will only be interpreting the output, but it can be valuable to have a high-level understanding of what it is that the computer and the software are doing. So let's explore that. In relative importance analysis, we're trying to overcome collinearity, which we can do by transforming the predictor variables so that they're no longer correlated. It's beyond the scope to go into what orthogonal transformations are and how they're derived. But what I want you to understand is that we can use an orthogonal transformation in order to produce variables that are not correlated. So what we do is we transform our existing predictors to new predictors through an orthogonal transformation so that they're no longer correlated with one another. After those variables are transformed, the transformed uncorrelated variables are used to predict the dependent variable. Then what we can do is take the standardized regression coefficients, transform those to represent the metric of the initial predictor, in order to get an understanding of what the relative importance is of each predictor. Now, Tonendal and LeBreton provide us with 4 steps in a figure which may help make sense of some things. Now, I want to highlight again that the computer is going to do all 4 of these steps. So you just need to have a high-level understanding of what's going on. In the first step, we're going to create the transformed uncorrelated predictor variables. Okay, we're doing that through the normal predictors that we have. We're just transforming them using an orthogonal transformation. In the second step, we're deriving a set of standardized regression coefficients by predicting the outcome variable using those transformed uncorrelated predictor variables. Okay, so what you're going to get from this step are these coefficients here. In the third step, we're deriving a set of standardized regression coefficients by predicting the transformed uncorrelated predictor variables using the original predictor variables. So we're getting these values right here. And then in the fourth step, all we're doing is multiplying those coefficients that we computed in step 2 and 3 in order to come up with the relative weight for each of these predictors. So the relative importance. So as an example, for x1, we would compute the relative weight, the relative importance value, by multiplying our coefficient here by our coefficient. We'd also then add the value that we would get by multiplying the coefficient that we derived here in step 2 with the coefficient that we derived here in step 3. And then the coefficient, once again, that we derived in step 2 here by the coefficient that we derived in step 3. Okay, so by adding those three values, we would get our relative weight, i.e. our relative importance for the x1 variable. Although multiple regression coefficients are biased by multicollinearity, the r-squared value is not. And because the predictor variables combine to fully account for r-squared, relative importance analysis permits us to uniquely attribute the r-squared explained by each variable to that variable itself. And likewise, we can sum the relative importance analysis values, and we will get the same value as that of the r-squared in the multiple regression analysis. Hence, the relative importance values tell us how much of the variance in the dependent variable can be attributed to particular predictor variables. Now, the relative importance analysis can be specified to include p-values and confidence intervals. So we can infer statistical significance using those. The problem is that the standard error is very, very small when we're performing relative importance analysis, and therefore almost everything comes up as being significant. And given the fact that we're often much more interested in understanding how much of the variance in the dependent variable can be attributed to particular predictor variables, significance is probably not the thing that we want to be evaluating most here. What we probably want to be evaluating and putting our emphasis on is whether the effect itself is meaningful. That effect, that relative importance value, is often going to be specified as being an LMG in software programs. And that's because Lindemann, Miranda, and Gold came up with some of these ideas. We can determine what effects are meaningful by applying Cohen's criteria regarding effect sizes. And so it's common to refer to LMGs that are greater than 2 as being marginally important, LMGs that are greater than 5 as being important, and LMGs greater than 8 as being very important. So if our LMG is 2 or below, we wouldn't consider it to be meaningful. Since the relative importance analysis effects permit us to uniquely attribute the r-squared that's explained to a particular variable, LMG should be 0 or positive. And we can use the correlations and the coefficients to infer the direction of the effect of a variable. I want to end by discussing some of the limitations of relative importance analysis. The first is the importance of being able to contextualize what it is that we're looking at. The relative importance value is certainly important and interesting to look at, but it doesn't tell us how easily or costly it is for us to alter a particular predictor variable. So that's something that we want to consider when we're making recommendations to managers. So a lower relative importance value for a variable such as price might be more meaningful than maybe a higher relative importance value for product, because price is something that we can change relatively easily, right? Once we have our product, there's a huge amount of costs for us to change that. Also, relative importance analysis, like multiple regression and many other statistical approaches, will not allow you to overcome incorrectly misspecified models. And that's why it's so important to understand the context in the variables that you're working with. Also, relative importance analysis assumes that your variables are not redundant. If you're including multiple variables in your analysis that have great conceptual overlap, for example, maybe store distance being represented by both miles and consumer drive time, Well, the variance explained by store distance is being partitioned across two variables. And so you're not getting a real true indication as to what that store distance contributes.